All right. So like I was saying just before I started recording the video, my intention today is just do a general review session, including going over this homework problem, because the results were a little bit all over the place. And I think we want to make sure we really understand the concept of per unit. And then I'll open up to any ever questions you have. So a couple things about doing a per unit diagram is you got to make sure you understand what you're trying to represent. And we're doing a per unit impedance diagram. So what we're really interested in is impedances and converting them to a standard and consistent set of bases. So if I zoom in a little bit, and I guess I can't do it that way. So let's just start at the top with these generators. You can see that 3 generators are on a common bus, and you've got breakers and all that stuff. So a typical one line has lots and lots of information because they want to be able to pull together a bunch of different things from the diagram. So in this case, there's more information than what's necessary on this diagram to be able to draw per unit. An obvious one are breakers. Whoops. Those don't have any impedances, right? I mean, a breaker should just be a short circuit or not a short circuit, an open essentially. So when you're drawing an impedance diagram, you wouldn't include any breakers on it because there is no impedance. It's an impedance of 0. These devices over here, a little hard to see. Those are called lightning arresters or surge capacitors. They're kind of 2 different pieces of equipment, but they essentially do the same thing. And the idea is they provide protection for the generators in the event of a surge from either lightning or switching. So under normal conditions, are those in operation? Are they actually functioning? They better not be, because that means you're experiencing surges, right? When they're conducting to ground, that means that you've had some sort of a high voltage condition on that generator, and you got to shunt that to ground. These are only designed to last for like milliseconds at most. Okay, so that would not be for continuous. We have the generator over here, and that has an internal impedance. This right here is called a field winding. So that's actually how you get magnetic energy. So that when you rotate, when you rotate the hunk of iron, you're actually rotating a magnetic field, not just a hunk of iron. And then over here, these 3 lines come together. And what you're seeing is you've got 3 phases, right? Because all these are talking about 3-phase generators. We have 3 phases, and they are being combined into 1 phase. What would be another way to call that? Or what would be another thing to call that or term for it? 3 wires connecting to 1 in a 3-phase system. It's the neutral connection, right? Remember, with a generator, you have 3 completely independent coils of wire located around the perimeter of the generator, and they're not referenced to each other at all until we connect them. And so you actually see the diagram showing all those 3 phases are connected externally and are connected to 1. So this is your neutral connection right here. And how much current should be flowing in your system under all the conditions we've talked about? Remember 3-phase systems when we looked at Y-connected systems? And if they're perfectly balanced, how much current is flowing? Because you have 3 wires that go into this common thing. We'll just show it as a ground for now. So I have 3 currents here. And this is IA, IB, and IC. What would those currents sum to? Because it's just a KCL, right? The sum of the currents into a node equal the sum of the currents out of the node. So the current going to ground or neutral is going to be equal to the sum of those currents. What should that be equal to in a balanced system? What is a balanced system? Yes, sir. Well, no, not exactly, because that just basically is like, that's conservation of energy, essentially. A balanced system means all the magnitudes are the same and the angles are off by 120 degrees, right? That's what we deal with a balanced system. So if we're dealing with a balanced system, vectorially, IN is going to be equal to the sum of IA plus IB plus IC. I'm right back to where I started. So the sum of the currents is equal to 0, isn't it? So the current flowing to ground under normal conditions is 0 amps. So in a balanced per unit impedance diagram, those grounding transformers don't even exist. Because they do have an impedance, but it doesn't contribute anything because there's no current going through them. So for the purposes of what we were trying to do with that homework assignment is we were just trying to show what would be the per unit impedance seen by a balanced system. So if I'm going to draw these on a per unit diagram, I have my bus, I have my generator, which has an internal impedance. Notice I didn't bother showing any cables or surge arresters or breakers. I have the generator voltage source, and that's it. Nothing else. There is no impedance connected to the, we'll call it the top side of the generator. So that generator we just drew is H5, and that is X generator H5. That's the internal impedance. Same thing for 6 and 7. XGH6, generator H6, HGH7, and generator 7. Those are all the impedances that you needed to show on this diagram, okay? I mean, we show the voltage sources in there as well because we need power at some point, but that's pretty much all our system has. Now, we're all done with this area. Now we're going to zoom in over here. And we see that we have a transformer. And a transformer is going to interrupt or impede the current flow through it. So that's XT86. And I'll show the transformer there for the time being, and I'll explain why in a minute. So that's the transformer impedance. Now we're going to go and we see that that breaker number is K80. Again, not an impedance device. But now we go to T85. So we have another transformer. Shown there. Okay? And again, I'm not including any cable impedances because unless you were trying to get really detailed fault current calculations, then you don't need cable impedances. There are some cases when you do, like if you're really trying to get exact currents, then yes, you would include that. But it's a lot of work and usually doesn't really have that much of an impact on your current levels, especially when you're going through transformers. All right, now we're on to this bus. So I got a 35 kV bus. So we'll draw that over here, move up a little bit. And that's our bus. On the other side of the bus is another transformer, T83. And when I look at XT83, now I'm at the 6900 volt bus, but I'm not actually going to show that as a bus, even though it's shown on the diagram, and there is a physical bus in the real world, but there's nothing else connected to it. So why would I muddy up my diagram and show another bus there if it's just going to muddy it up? I see that it's going to generator HH, which looks awfully similar to 5, 6, and 7. So my diagram is going to have HGH8 and generator H8 right there. And that's all you could do for the diagram because look over here. Any impedance devices over here? Nope. VCB, if you don't know what that stands for, that's a vacuum circuit breaker. Anybody know why you would use vacuum for 35 kV? How well does electricity flow in the air? Not great, but it can, right? There's stuff in the air. We see lightning. How about under vacuum conditions when there's no air in there? You pull a vacuum on it, there's no material for the electrons to flow through it. So when you pull a vacuum, and you can't pull a perfect vacuum, right? Because that would take an enormous amount of pressure. But you pull a vacuum to get all the stuff out of there, and literally it just opens and closes under vacuum conditions. And so your spacing can be very small. Where if you did it in open air, you'd have to have much bigger space. So under 35 kV, vacuum breakers work really well for medium voltage conditions like 4160 and above. Below that, you usually just use open air because that's not too big of a deal. But this is using vacuum. But again, it's just a breaker. And then it goes to no man's land, so we're not even going to worry about it. So this was essentially what you needed to create, at least from a base level. Yes, sir. Good question. So would vacuum breakers work at really high levels, voltages? Yes. If you could pull a perfect vacuum, right, where there was nothing in there whatsoever, then it would work. The problem is that the amount of energy, and this has to be sealed, right? So this is under vacuum. So then you got to seal it to keep the vacuum in there. And the amount of pressure, it would leak. It just wouldn't work. So typically what they use after 35 kV, they use sulfur hexafluoride. It's a gas, SF6. And then you can get any voltage you want. So all the higher voltages go with sulfur hexafluoride. But it wasn't that long ago, they used to use oil, because oil actually is a pretty good insulator. So they would use oil breakers. And even before that, they actually had air breakers. They just had huge breakers for 345. They had these massive arc chutes, like with just big concrete things, so that they could blow arcs in them. It took a lot of space and a lot of effort, but that's what they used to do. But now everything is modular. It's like the size of this desk. You can actually put what's called GIS, gas insulated. That's the SF6. You can put it inside of a room like this, and it would be a 345 kV, and you can walk in and it's all grounded. It's perfectly safe. So when you're in fancy towns, like nobody wants to see overhead lines, they either do a vacuum. Sometimes they do open air, or not open air. They would do vacuum. They would do air if it's a low enough voltage, or SF6, just to kind of keep it looking prettier. Yes, sir. Yeah. So the tripping of the breaker has more to do with the mechanisms, the mechanical mechanisms that force the contacts open. But clearly you need beefier equipment if you have to open this bar as opposed to opening this bar. So there's a lot more mechanical stresses and strains, which means you need a lot more mechanical oomph to be able to open those breakers. So another reason why SF6, you can just have easier, simple pieces of equipment. Okay, so I left the transformers in, and I said this was a per unit diagram. So Paul, why would you put transformers in? Well, the reason why I put transformers in is we have to identify the areas where we have a change of base, correct? That's what the transformers do. They change the V base and I base and Z base. So we just do our dashed line. Maybe I'll just pick a different color. So every time we go through a transformer winding, we have a different base, right? So we have region number 1 up here. Down over here, we'll call that region 2. Over here is region 3. And that's region 4. So it's helpful to include transformers when you're building your per unit diagrams, so you know where you're going to have your change of base quantities. So now I'm going to redraw my diagram. Very simple without the transformers. So I have H5, and I'm just going to call this X5 just to make it a little bit easier to write. X6, 6, X7, go on to a common bus. Out of that bus, I go to, I'll just call it X86, X85, over on the common bus, X83, X8, and H8. Okay. So now you know where your regions are. You know what the diagram needs to be. So now you start specifying. So you pick S base equal to 100 MVA. And over here, and you may want to put on this diagram, I picked V base in region 1 to be 6,900 volts. To get VB2, that's 6,900 times the turns ratio. So go back to my original diagram, and I can see that that's 7,200 over 480. So that multiplies by 480 over 7,200. And that's the V base over there. For VB3, I know my turns ratio is 6,900. Whoops. To 34.5. But which V base should I be using? Should I be using V base 1 or V base 2? V base 1, yeah. Because V base 1 is the base where the transformer T85 actually steps the voltage up. So I'm not going to use V base 2 because that transformer, the T85, has nothing to do with those areas. So it's completely independent. So that's going to be 6,900 volts. And over here, VB4 is going to be equal to my 34.5 kV multiplied by 6,900 over 34.5. I've got S base, I've got V base for all 4 cases. Now, all I need to do is X H5, X H6, H7, H8, and then I had, is it 85, 86, 85, 83. Now I just have to put those under a common base. Let's start with the transformers because those are the easiest. X83 is right on the sheet, and that tells me it's 5 3/4% Z. So that's 0.0575. But notice it is at either 7,200 or 480 for the V base, and the S base is 500 kV. So I'm going to be doing VB old. Do you want the low voltage side or the high voltage side? I don't care. Let's do the low voltage side. So the low voltage side is 7,200 divided by 6,900. That quantity squared. And then I multiply that by SB new over SB old. 100 M divided by 500K. And that's all you needed to do for X83. X85 is, let's see, that's a base rated of 15 MVA. So we usually use the 15 MVA, the base rating. So, oops, I forgot to write the impedance. It is 5.5%. Times, and it doesn't matter. These voltages are the same. So it doesn't matter if I'm on the low or the high voltage side. I'm just multiplying by 1 squared, right? And that's going to be SB new over SB old. And then T86 is, whoops, I did it backwards. This should be 86 up here. That's 86 and that's 83. I read the wrong spot. Sorry about that. So T83 is going to be 5.41. And the voltage again is 6,900 over 6,900. Or you can use 34.5 over 34.5, right? Those both equal 1. And then that's equal to 100 MVA over 5 MVA. And those are your 3 transformers. And I kind of wrote sideways, so let me move this to say this is equal over here. So let's go to generator H8. And over here, is the data. And normally we're going to be picking our saturated values. And for those, yes, sir. Yep. So you always use the lowest rating, which is called the base rating. Why? Because you can put fans on it and get additional cooling. So the lowest rating is natural cooling, like no fans on it. The second rating is now we force fans on the radiators. And what does that do, right? It helps reject heat faster. So you can run it at a higher power output and still not exceed the insulation temperature rating. And then you can switch on another stage of fans and get even more power out of it. So that's pretty common. Like if you remember the data sheet when we did the test, we needed to get the X values for the R equivalents, RCs, all those. But that was 60, 80, 100, I believe, was the rating for that. And so that's pretty common for bigger transformers. You have multiple ratings on it. That just means you're putting some sort of cooling mechanism in there. Okay.
Hey, Paul.
Yes.
Before you go on, am I reading the one line correct that the transformers and the generators are all based on 6,900 volts?
No. This one is 7,200 and 480, right? Everything else is 6,900, but that one.
Okay.
Right? So remember where you get the original equipment ratings, you get them from the nameplate. This nameplate transformer it takes 7,200 volts and steps it down to 480.
Okay, I was thinking that you were talking about T83 and it's at 6,900
Yeah,
volts.
I think I said that incorrectly, but then I swapped these around, right? I call that
okay.
83.
Yeah, it was just the one transformer that changes base.
Correct. Well, it changes voltage base. All the transformers change power base, right?
Correct.
Okay. So now there's a lot of data here. And it depends on what you're trying to do. In many cases, if you're doing a fault analysis, you'll use what's called the direct access transient reactance. Okay. I know that doesn't make a lot of sense to you all. It will very shortly once we start looking at fault current contributions. But if you look at the numbers, right, if you look at the saturated XD versus XD prime, you can see XD prime is lower than XD. So if you had to guess, out of those two, which one is able to produce more fault current? XD or XD prime? Or you're not sure? The answer is XD prime, because when you divide a voltage by a lower impedance, if I take 35 kV and divide it by 0.26, I should get a lot more current than taking that same voltage and dividing it by 0.75, right? May not be obvious, but you're dividing by a smaller number, so you get more current. So it just depends on what you were trying to do. If you're trying to do a fault analysis, where you're trying to figure out which current is going to be interrupted, usually XD prime. If you want to look at a longer time frame, you use your XD. And if you want to see what the system has to what's called withstand, like fault current is the highest, usually just after a fault occurs, but then it decays as a first order time constant. It decays pretty quickly to those lower values. But you can see XD double prime is 0.018. So that's going to give you the highest amount of fault current there. So you grab from whatever parameter you want. I'm just going to put XD in here. And you decide, again, what condition you're trying to do. Are you trying to do fault analysis, breaker withstand, or more of a steady state voltage drop? And then I'm going to do VB old. So I got to go up over here, but it does tell me right here what the VA base is, but it doesn't tell me the voltage base. You can get both those numbers right there. So this is in region 1. So 6,900 over 6,900, that quantity squared, and then we multiply it by SB new over SB old. And that's how you convert that impedance. H7, 6, and 5, I think they're all the same if I remember correctly, but let's go to the data sheet. And that's right here. So these are old generators. I know a lot about this project because I actually did all the relay settings for generator H8. They completely rebuilt it because if anybody knows, does anybody here have Pulp and Paper Foundation scholarship? One person? Do you know what the mills used to use for power up in Millinocket area? Used to be 40 hertz. So they built all these really extravagant power distribution systems with 40 hertz systems because that's what their mills operated at. But those mills aren't in operation anymore, but they've got really great hydro resources. They got big dams that have been reasonably well maintained, and they basically can buy these places for pennies on a dollar, but they can't connect them to the grid unless they convert the 40 hertz to a 60 hertz. So before I showed up, they had a variable frequency drive that would take 40 hertz in and dump out 60 hertz. So they realized that was just a nuisance. And so they actually rewound this generator so that it operates at 60 hertz. So that's why if you look at this data sheet, it's from 2018. And it actually tells you it's designed to operate at 60 hertz. The other ones were done earlier than that, but it was worth it for them to go ahead and do a major upgrade to put in this new generator. They just took the old generator and just rewound it essentially. So that's how they did it. But if I go here and look at the data, you can see that I've got different MVA ratings. So those are the base quantities, right? You can see 6,900 volts and one unit at 6.6 and the other two at 5.2. Notice this one even here still says it's 3.9 MVA at 6,900 volts, but we're not going to worry about it. We don't care about the excitation system. These are some generator ratings, some values, but if you look down over here, we have our transient reactance. That's that XD value, XD prime value. So the value that I would have picked, I would have had to pick XD prime or XD double prime. I wouldn't have been able to use the steady state one because I don't have any values that tells me steady state, right? So I would use this data over here. So for generator number 5, this is going to be equal to 0.32 or 0.32? 0.32. So 0.32 times the voltage, 6,900 over 6,900, quantity squared, and then my SB new is 100 MVA, divided by, I think this one was 5.2. Nope, this one was 6.6. And that's how you converted that impedance. These other two, I think, were both 0.28. So 0.28 times 6,900 over 6,900 squared times 100 MVA over 5.2. And that is equal to X6, not G. And that was the per unit diagram, converting everything to per unit on a consistent base. And we sort of did the whole process, right? We identified S base, one V base, and then we calculated all the V bases. The extra thing that we had to do here is we had to go ahead and get the data, and that's what you'd have to do in the real world. Somebody's not going to say, here, convert this diagram to per unit. They're going to say, go get me a diagram in per unit and make sure it's all on a consistent base. So you're going to have to retrieve all the data to put it together. And then when you're done, you draw your diagram here. And now you can do all kinds of things for it. But the very first thing you should do, calculate Y bus, right? So we'll call that bus 1, bus 2, bus 3, and here is bus 4. Or would you rather call it bus 3? I would probably call it, I would probably call it bus 4 because they're separated enough and it's not a big deal to add a fourth bus in there. So my Y bus here is going to be equal to 1 over x5 plus 1 over x6 plus 1 over x7 plus 1 over 86 plus 1 over x85. That's my first Y bus. My second one is the negative of the admittance between bus 1 and bus 2. So negative 1 over x86. The third is the negative between 1 and 3. Negative 1 over x85. And the fourth is the negative between bus 1 and 4, but there's no connection. So that is 0. So that first row becomes my first column because the transpose is the same. Now for bus 2, I only have one element. Oops, let me move it over a little bit so it doesn't look like it belongs over here. Notice no negative sign. Now I'm going to go the negative 2, 3. And there is no connection to bus 4. So rows become columns. Now for bus 3, I've got 2 of them. x85 plus 1 over x83. Yes.
2 and 3.
Oh, 2 and 3 are not connected. Yeah, you're right. That should not be there. 2 and 4 are connected. Thank you. So that is 0 and 0. So 3, I have those two, and then I have minus 1 over x83, minus 1 over x83, and then over here to bus 4, I have 1 over x83 plus 1 over h8 or 8. And now I can really do magic. I've got the Y bus representation of my system. I can do a ton of calculations. I can do voltage calculations, fault current calculations. I can do some power stuff. We'll call that load flow, and that'll make sense pretty soon here. But I can do a ton of work just based on having this Y bus. And you've got to do it in per unit because you cannot build Y bus when you have transformers in your system, because there's no way to reflect the impedances back and forth. It's too confusing. But to do it all in per unit, they're just impedances, they're just numbers. It's no transformer. All right, does that help explain? I added a little bit more for the problem. I added in the Y bus stuff, but eventually you would need to build Y bus. So it behooves you to go ahead and to see this process. But I want to make sure that you all see how to do that. Because like I said, there was a lot of mixed attempts on the homework. And I know it can be frustrating at times when you're trying to look through all this data. But again, I'm trying to prepare you for perhaps what you'd be looking at. And this is actually a very simple data sheet. A one-page data sheet is unheard of for many power systems. But they probably got it for the generator for cheap. So, yes, sir.
Where did go back to where you calculated for the transformers? You multiplied the
Here or
no, the first multiplication. How do you find the 0.0575?
it's right on the diagram. If you look here, it says 5.75%.
Right. So that little that little attachment part below that below that part is very okay.
I guess I'm not following you. The attachment part?
Like yeah, I think yeah that part there though.
It's the there's a 5.75% listed right there. Under
Oh, okay, that one.
I can try to clean this up. If that helps.
I added into the.
Yeah, those were actually on the actual one line. Because you oftentimes don't get impedance data for small transformers. Usually what you're gonna do is walk out and look at the nameplate, take a picture of it, and actually record it. And that's actually what I did on this one, because this is the project I had to do. Like I said, I had to do a fault diagram because I had to calculate fault current so I could do the settings for the generator. So that was my work a few years ago. Other questions?
Just a comment, Paul. The last page of the handout that shows the generator data,
Yeah.
that's where I got confused. You did have some arrows at the direct axis, steady state, and then the transient, and you had it circled. And so that's where I got the value for 0.75 for all the generators. I should have known to use the transient ones up.
Well, the only
higher.
reason why it would have been very difficult to use that value, but then to go over here and you don't actually have the steady state values, right? So your per unit diagram would have been very confusing. Is it steady state or is it transient? So maybe if you had marked up saying these are transient and these are steady state, it's just the diagram would have had two different representations. And so if you would have added that note saying, I use the two different ones, you probably would have been fine. But you know, what happens is that when you're doing these diagrams, they got to be based at the same time frame, if you will.
Yeah, I just misunderstood whenever I think in class you said use that one, the saturated, and I thought that you meant use the one on that for every machine. And so I didn't use the ones there that I should have used.
Well, over here, I don't think it has steady state impedances, does it?
No, and that's what I'm saying is
Yeah,
that
okay.
I know from experience the values on that one, it's really high compared to what we actually use. But anyway, so that's where I got off, and that's where I got the value for 0.75 for all three machines.
Well, it definitely would not be for all three machines unless you said, hey, I can't find the steady state data for H5 through H7, right? But this data sheet, it's hard to see, but if you look right here, that only applies to generator 8.
Okay.
The data over here, I even said in the title, well, I don't know if I would have said it, but you can see it does have some number 8 information, and I probably would have been okay if you did it, but I gave you a separate data sheet, a much more updated data sheet. And so the hope is that you said, yeah, this is just a newer generator. That's all it is. It's a replacement generator. And if anybody wants to see, if you're interested, I can tell you where these generators are located. It's really odd to go there because to access the place, you have to drive. Oh, come on. You have to drive off the road. And it's all locked up, but like nobody is staffed there. It's not that one. It's going to be further downstream. Oh, where is it? It's next to the road. Maybe it's East Millinocket. Here it is right here. It even says Dolby. So inside this building right here, let me mark it up. Oh, doesn't want to let me mark. Okay, sorry about that. Right there. It's very difficult to see. Actually, no, that's the control house. The generator is right here. The substation you can see right there. You see the substations right here? That is basically the substation. Oh, come on. So if you were be able to walk there, that, what you see here is physically represented right there. Looks a lot different on paper than in whatever. I'd love to do a tour of the place, but like I was saying, this is a dirt road and there's a fence. I think it's right here. It's either here. Yeah, I think you can see the fence right here. So they just have a lock and it's hardly ever staffed, but it's not easy to get into unless you break and enter. So it's not an easy thing, but it's an old hydro plant and still runs great. All right, any questions on this or other questions? Like I said, we don't really, this is not a great time to have a lab, but next week we don't have lab at all because next week is October break, right? So next week there's no lab because there's no class or no school that day. But I wanted to make sure you all had an opportunity. So I'm not sure when we're going to fit in the transformer stuff. I mean, the T-line modeling stuff. I just have to figure that out. But I did update the syllabus so you can take a look and see the dates. So questions? Any questions from TV land? Like I said, I don't have a lot of new material, right? Because we just got a test and we only had one new class. I'm not sure why this is moving, but there's a gremlin.
So is X prime D generally how it's listed on schematic?
It would be X prime D, yeah. Sometimes they leave out the D because that means direct access. If you look back at the data sheet, there is something called quadrature access. That's what the Q stands for. And that's a little bit more modeling and it's more detailed than we want to get in the class. But if you go back to your math classes, when something's in quad with something, that's 90 degrees. So when you do what's called, it's called Parkes transformation, when you get this rotating magnetic fields, you actually use your direct and quadrature access for that. But that's usually graduate level stuff. It's not really appropriate for this class. Nothing in TV land? All right, well, enjoy your extra minutes today. Have a wonderful day, and I will see you all tomorrow. Take care, everyone.